Okay, good morning. So we continue the topic of complex numbers, the exponential form. So if this is finished, there is only one part left, which is not directly related to complex numbers, but it is covered in this chapter. So I skipped that one. I finished this one, then this chapter is completely finished. So today we want to talk about the exponential form of a complex number. So far we had two forms of a complex number. One of them is the standard one, and the other one was the polar form or the trigonometric form. But now we want to talk also about the exponential form. This is a famous formula. I don't want to prove it, but if I just write the formula in front of you without any motivation, it's not probably a good idea. So let us try to motivate the formula that I want to write here. Okay. So my goal is to show that if theta is a real number, then the Euler number E to the power of I theta, okay, is equal to cosine theta plus I sine theta. Okay. Uh, so this is called the Demoir's formula. Uh, I will write the name later, but this is what we want to actually motivate, because the real proof of it is not at this level, but if I just write the formula there without any motivation, probably it's not a good idea. So what we do, I define a function here for you. So f of x, so let me write f of theta to be e to power I theta. And then I define another function g of theta to be cosine theta plus I sine theta, yes? And if you remember, I told you that we want to keep the rules of the game as before. We just added one new rule to the game, and that was I squared is equal to minus 1. So let us pretend that the notion of derivative makes sense and it follows as before. So what I will do, I will take the derivative of this function, g. I'm just trying to motivate you why might be this formula relevant. I'm not proving anything, okay? I'm just trying to motivate you. So let us take the derivative. So the derivative of cosine theta is minus sine theta, and then the other one becomes I cosine theta. But it already indicates that this theta should be in radians, yes? So this is, be careful. In the polar form, it didn't matter if theta is in degrees or in radians. But when I am saying that the derivative is this one, do you know that the derivative of cosine becomes minus sine, the derivative of sine becomes cosine if and only if theta is measured in radians. So I'm implicitly assuming that my theta is in radians. Okay? And now what I do, I will take I out from here. And then what happens? This becomes just simply cosine theta, but this one becomes minus 1 over I sine theta. Yes, why is that? I multiply it back, I and I are cancelled, so it is minus sine theta, that's correct. I multiply I here, so that's correct. But do you remember what is 1 over I? 1 over I is also equal to minus I. Yes, do you remember that? 1 over I is minus I. So minus 1 over I is nothing except I. So what I can do, instead of minus 1 over I can write I. Do you agree? Okay, but this is exactly the same expression. So if you don't mind, let me write it the other way around. So I have this I here. I have cosine theta here. I would write I sine theta. So what I did, and this is the same function. So this is nothing except g of theta. Yes? So what happened, I called this side g. I differentiated with respect to theta. I realized that g prime theta is equal to I g theta. Yes? So g prime theta is equal to I g theta. But let me divide both sides by g theta. then I will have this. Yes? Okay, but is the left-hand side familiar for you? The derivative of a function divided by the function. It is the derivative of a famous function. Yes? What? No, not e. It's related to e, but it's not e. No, no, no. It's ln. It's the derivative of ln of g of theta, yes? Do you remember? So the formula for the derivative of ln of x was what? 1 over x. This is the formula for ln of x. But I told you that if you have ln of u, according to the chain rule, it follows the same rule unless you have to multiply by an extra u prime, which becomes u prime u. This is a very important combination. Remember it. Sometimes in the national exam, they will ask you questions about this. I will solve some of them for you when I'm teaching you the notion of integrals. But whenever you see a combination like this, a fraction whose numerator is the derivative of its own denominator, then remember that that combination can be written as the derivative of the ln of u. So this is exactly that combination. Do you agree? Because whatever I have in the denominator, its derivative appears in the numerator. So I can write it in this form. Yes? And that is exactly equal to I. Now, I am telling you this is a function whose derivative is I, and I is constant, let us assume. So what can you say about the question mark? What is the question mark? What is the most general form of the question mark? Give me let me see, I give you a function whose derivative is 5. So what is that function? 5x plus any constant. So I need a function whose derivative is I. So what can I say about the function? Not x, because variable here is theta. Yes, so it becomes I theta plus a constant. Yes, and then what happens if ln of a function is equal to this? What can I say about this function? So it is like this: ln of a box is equal to 7. What is inside the box? E to power 7. Yes, so ln of something is this, so that something is e to this power. Do you agree? Yes? Okay, so what I can do, I can say that g theta is equal to e to the power of c, e to the power of theta. But e to power c is also a constant. Yes, c is a constant, e is a constant, so e to the power of c is a constant. So if you don't mind, let me call that constant a. So I am introducing the constant a to be e to the power of c. Okay, so this is g theta. But what is this part? This part is f theta. So what I realized that g theta is a times f theta. So at least I was able to convince you that whatever this function is and this function, they don't differ that much. One of them is a constant multiple of the other. Is that right? But I want to show that no, they are exactly equal. So I want to get rid of this a. In other words, I want to show that a is exactly 1. So how can I do that? That's also simple, because this formula that I got is independent of what the value theta is. It is valid for all possible values of theta, including if I choose theta to be 0. So then, because this formula is valid for all theta, if I want to find a, I just need to calculate the left and the right for one particular case that I can calculate. So I choose 0, then this becomes this. But now if I ask you what is g of 0, it's not hard to calculate. G of 0, replace theta with 0. Cosine of 0 is 1. Sine of 0 is 0. So g of 0 is 1. So g of 0 is 1. The right-hand side, I still don't know a. But what is f of 0? It's e to power 0. And e to power 0 is also 1. So what is A then? A is 1. If A is 1, put it back here. Finally, hopefully, I could motivate you at least. This is not unreasonable to assume that these two functions are the same. Okay. And this formula is a very famous formula. Okay, so, and that is called De Moivre's. I always forget the spelling, it's a French name. Then I should check it there. Let me check it first. Okay, anyway, so this is called De Moivre's formula. So De Moivre's formula tells me that E, the Euler number that you learned from even Math 3C, I theta, theta is a real number. Let me emphasize theta is in radians. Then this becomes cosine theta plus I sine theta. Yes, this is a very, very famous formula in the theory of complex numbers. Is that okay? For example, if I ask you, what is e to the power of I times pi over 4? So I can ask you a lot of questions. For example, I can say that what is the standard form? I can ask you what is the argument. I can ask you what is the real part, what is the imaginary part, because at the end it's a complex number. Whatever I could ask about a complex number, I still can ask about this number. But if I want to answer those questions, you have to be able to write it in a standard form or polar form to answer that. So what happens? It becomes cosine according to that formula pi over 4, and then I have plus I sine pi over 4. And then of course cosine pi over 4 is 1 over a square root of 2, the same for sine. So this becomes this. For example, they might give you this and they ask you what is the real part. Okay, so what's the real part? 1 over square root of 2. They might give you this and they ask you what is the absolute value of this number. Okay, so you can write it in a standard form, and absolute value becomes this 1 to power 2 plus this 1 to power 2, which becomes 1. But of course, this is always true. What is e? What is the absolute value of e to the power of I theta always? The absolute value of e to the power of I theta for any choice of theta. This is the real part and that's the imaginary part. So this becomes square root of the real part squared plus the imaginary part squared, yes? And this is always 1. You remember what was the name of these type of numbers? In mathematics, if a complex number has absolute value 1, it is called unimodular. Yes, its modulus is 1. And in physics, they call it a phase. Okay, so if you see phase in physics, this more or less means this. Okay, any questions? Is that understandable? Okay, but now you see that. Do you remember the polar form? Now the polar form can be written very compactly using this exponential function. So if I give you a complex number in the polar form, it is r cosine theta plus I sine theta, yes? This number is the absolute value of the complex number, and this number is the argument. But because of the De Moivre formula, this expression can be written compactly in this form. So if I replace that, this becomes z equals to r e to power I theta. And this is called the topic of today's lesson, the exponential form of the complex number. So r is the absolute value and theta is the argument. Yes? So this is called the exponential form of the complex number. So I don't remember is it in the formula sheet or not. But more or less, I'm sure that the Demoir formula should be there, so it would be a matter of just 1 second to write the exponential form if it is not there. Yes? But the good news is that you really don't need to memorize anything when you have it in exponential form. Yes, for example, if I give you two complex numbers into polar form, so for example, if I have z here and w, let us write it as another number, let us say s cosine phi plus I sine phi. Yes, if I ask you what is z times w, if you don't remember the formula, then you might be in trouble or you have to start from scratch. Yes, what was the formula? Do you remember? It is rs, the absolute values are multiplied by the arguments are added. Yes, so if you don't remember this rule, you might be a little bit in trouble. But hopefully, when you write it in exponential form, you don't have that problem anymore, because I hope that you remember the formulas for exponential forms. So let us say that z is written in the exponential form, and w is also written in exponential form. Yes? And if I ask you multiply z by w, what do? You don't need to remember something. So you just say that I want to multiply. I multiply this number by that number. So of course R and S will be multiplied. There is nothing to remember. And you know the rule. If I am multiplying two exponents with the same base and I add the exponents, yes? So I am multiplying e to power I theta by e to power I phi. So this is even in Math 1C. So if I have two exponents, two powers with the same bases, I write the same base and I add the exponents, yes? But when I add the exponents, I can factor an I out, yes? So this is very simple to see that this can be written in this form. So working with complex form is extremely simple and straightforward. So this is why usually either people use the standard form or the exponential form rather than polar form, because it will, for example, do you remember what was the benefit of writing a complex number in the polar form? Hmm? To raise a high power. But the raising high power in the exponential form is also extremely simple. Yes, because if I give you this and I ask you to raise it to power 100, for example, what do? You write r e to the power of theta to the power of 100, and then r to the power of 100, and then this to the power of 100. Let me write the details, but you don't know to do that. In principle, I can do that because that's a product. But no one needs to remember what happens here. It becomes r to the power of 100, and then what do? You just multiply the numbers. Do you agree? So it becomes 100 I theta. So let us solve one. So you see that what I'm saying is that whatever the polar form can do for you, the exponential form can also do for you. The good news is that you don't need to remember anything for the exponential form. Yes, because more or less all the formulas that you have are as before. Okay, for example, I mean, this is not probably very necessary, but let us do one example in this form. Okay, for example, let me write z equals to square root of 3 plus I, and I ask you, so what is z to power, I don't know, 1200? Something like this. So, of course, now you have two alternatives. Before today's lesson, if you see extremely high power of a complex number, it is an indication that you have to switch to the polar form. But now, if I were you, I prefer to switch to the exponential form because at least it's more compact. But still, for that, I need two ingredients. What are those? I need the absolute value. Yes? So if you see the formula here, I need r, which is the absolute value. I still need theta, which is the argument. But it is extremely important in the polar form, It doesn't matter if you express theta in degrees or radian. That is the only exception that you have to respect. But if you want to use the exponential form, you have to write it in radians. Degrees is not acceptable. Okay, so what I do, first of all, I will actually calculate absolute value of z, which is r, and it becomes square root of this number to power 2 plus the imaginary part to power 2, so it becomes 3 plus 1, 4, square root of 4 is 2. But then I need to find the argument. So what is the argument? Do you remember, I always calculate tangent alpha using the formula of absolute value imaginary part divided by the real part. Yes? So imaginary part is what? A 1, and the real part is this one, so the absolute value is this. And this is one of the famous numbers, I have it in my memory. So alpha becomes tangent inverse of this, which is pi over 6. But here, because this is in the first quadrant, you remember this? In the first quadrant, theta is alpha. In the second quadrant, theta is pi minus alpha. Here, theta is pi plus alpha, and here, theta is 2 pi minus alpha. Yes? So because this is in the first quadrant, because both real and imaginary parts are positive, so it's in the first quadrant, alpha and theta are the same, so theta becomes what? Theta becomes pi over 6 as well. Okay, so now instead of writing it in polar form, let us write it in an exponential form. So exponential form is r e to the power of I theta. So z becomes what? R, which is 2 e to the power of I pi over 6. Very compact. And now I raise it to power 1200. Of course, if I want to raise it to power 1200, this should be raised to power 1200. But then what happens here? And then these two exponents should be multiplied. But when I multiply them, what happens? Pi over 6 times 1200. It becomes what? 200 pi. Yes? So it becomes e to the power of 200 pi. I 200 and pi. Okay? But then you have to calculate this. If you leave it like this, this is not acceptable. And then this is where that Demoir's formula is useful. So what can I write about e to the power of I 200 pi? This is nothing except cosine of 200 pi, because 200 pi is playing the role of theta. Okay, but these are hopefully simple. So what is cosine of 200 pi? What? 1. Because 200 pi is the same place as 0. Yes, I have 100 complete revolutions. Yes? So cosine is 1, sine is 0. So this is nothing except 1. So the answer to this becomes 2 to the power of 1200. Okay? Okay, so there is another thing that I forgot to say. Many people say that this is the most beautiful and elegant formula in all mathematics. And that is the case that you choose theta to be pi. Yes? So if you choose theta to be pi, let us see what happens. If I choose theta to be pi in the Demoir's formula, I will have this one equals to cosine pi and then plus I sine pi. And e to the power of I pi becomes equal. Cosine of pi is minus 1, but sine of pi is 0. And then they bring this to the left, so it becomes e to the power of I pi plus 1 equals to 0. Probably they say that this is the most elegant formula, because there are, you see, 1, 0, I, pi, and e are fundamental constants of mathematics, and all of them appear in the same equation. So many people say that this is the most beautiful equation of mathematics because is very simple, and it is connecting more or less all fundamental constants in mathematics into one single equation. So that's good to know about it. Okay, so let us now try to ask you some questions. So far, what type of number is this? Do you remember the name? You also had it in the book. So if you have I times theta, if I have a complex number in general, I can have b to be 0, then I have z is equal to a. I can also have a equals to 0, then z becomes bi. So in this case, I would say that z is real. Do you remember what was the name of this? Yes? Pure imaginary. Okay? So this is telling me if I have a pure imaginary number, I know what is the meaning of e to the power of I theta. But what is the most natural question coming after that? Is that if I have a complex number which is not pure imaginary, okay, so for example, what happens if I have e to power any z, and z is not pure imaginary, is, for example, let me write it as it is written in the book. I want to understand what is this, okay? But this is, I'm not proving anything, this is the definition of a complex exponential function. I want to define this based on the previous knowledge I have about exponential functions, because I told you I want to keep the rules of the game the same. So what do you think I will define? In other words, my question mark is e to the power of x plus yi. What do you think is a good definition of this, which is consistent with all the rules that you have learned so far, and it is also consistent with this? In principle, I can just simply define it for you because definitions don't need proof, but it is better to motivate why definition is good. So for example, I hope that you understand that the Demoir's formula is not directly applicable, yes? Because the Demoir's formula is directly applicable for the cases in which the exponent is pure imaginary. But this is not pure imaginary. But I told you we want to keep the rules of the game the same. So what can I write for this if I insist to keep the rules of the game? I can split it into how? E to power x multiplied e to power iy. This is nothing mysterious at all. Why? Because e is the famous Euler number and x is a real number. So if I ask you what this is just the normal exponential function that we learned in Math 4 as well, before this and in Math 3C. This part, can I use the Demoir's formula for that part? Yes. So this is the definition. Yes, so that's the definition of the exponential function. So if z is equal to x plus yi, if someone asks you what is the meaning of e to power z, by definition, semicolon means by definition is equal to this expression you see, e to power x cosine y plus I sine y. Yes. Or if I just want to write it in terms of z, can you tell me how to write it in terms of z? Don't write x and y. Can you write the same formula only in terms of z? It becomes equal to what? E to the power of x. But what is x? The real part of z. So if you want to express everything in z, it is possible, but it becomes ugly. So it becomes what? E to the power of real part of z multiplied by cosine of what? Imaginary part of z plus I times sine of imaginary part of z. Yes? It is a little bit ugly, but that is what it is. Okay? Any questions? So for example, in the book, they might give you this. Um, so for example, let us say, what is the imaginary part of this complex number? E to the power of 3 plus pi over 3 times I. We want to answer this question. Yes? So you see that this is the new lesson, yes? Because 3 plus pi over 3I is not pure imaginary, so I cannot just use the Demoir's formula. I have to use the new definition. Yes? Okay, so what should I do now? So if I want to answer this question, I have to understand what is this one. So e to the power of 3 plus pi over 3I. How can I calculate this? It is on the board. Yes? Here, 3 is playing the role of this x, pi over 3 is playing the role of the y. So this formula is in front of you in the formula sheet, so you put it there. So it becomes e to power what? 3 multiplied by cosine of pi over 3 plus I sine pi over 3. Yes? But e to power 3, just leave it like this. But what is cosine of pi over 3? I have it in my memory, so it's 1/2. And that one is a square root of 3 over 2i. And then you multiply it in. So it becomes e to the power of 3 over 2 plus e to the power of 3 square root of 3 over 2 times I. Yes? And now the question mark is, what is the imaginary part? So what's the imaginary part? E to power 3 square root of 3 over 2. Okay, so let us try to understand a little bit about this formula. Okay, I want to test your understanding. I mean, this is not, might be you find them in the exercises in the book, but let me try to ask you about these things. One thing is that if I ask you, z is a complex number, I don't know if it is pure imaginary, if it is real, or it contains both of them. Now my question is that, can I say something about this in general? Yes? E to power x, which x is what? Because you cannot write e to power x. People can say, what is x? X is the real part. So if this is wanted, you can immediately write e to the power of real part of z. But why is that? Because we just learned that if I want to prove this, I would say let z be equal to x plus I y. Okay, and then e to power z becomes, according to the definition, becomes e to power x times cosine y plus I sine y. Agree? And then, of course, if I want to find the absolute value of a complex number, I need to know the real part, I need to know the imaginary part. In order to do that, I have to multiply things in. Sine y. Yes? This is e to power z. Okay, now if I ask you what is the real part of e to power z, you will show me this. What is the imaginary part of e to power z, you will show me this. So if I ask you what is the absolute value of this, you will say square root of the real part squared, yes, plus the imaginary part squared. Of course, I could do it much simpler, but the reason I just want you to know this was as well, okay? This one as well. So now if I raise it to power 2, this one becomes to power 2, which becomes e to power 2x cosine squared. This becomes e to power 2x sine squared, but I can factor e to power 2x out. So it becomes cosine squared y plus sine squared y. But what is this one? This is 1, and this is e to power 2x. But the square root of e to power 2x is nothing except e to power x. But what is x? X is the real part of z. But I think you calculated in your head differently because you could answer it quickly. And that is another way to do it. Because if I ask you, do you remember we had a formula that if I have two complex numbers and I ask you what is the absolute value of the product, this becomes what? The absolute value of the first one times the absolute value of the second one. So if I ask you what is the absolute value of e to power z, this is a product, yes? This becomes the absolute value of the first one, absolute value of the second one. But I just told you, I think I erased that, but this is a phase. So the absolute value of the phase is 1. But do I need this absolute value? So this is just nothing except 1. But absolute value of e to power x is what? Yes, why? Because x is real. So e to power x is the old familiar exponential function. And we know that the exponential function in the real numbers cannot be negative. It's always positive. So I don't need the absolute value sign. So do it in any way that you like. Okay, so this is good to not to remember. I mean, if you want to understand a little bit deeper about complex numbers, these kinds of things you should be able to be comfortable with. But now let me ask you another question. Do you remember we had some formulas about conjugation? For example, I told you that if I have two complex numbers, it doesn't matter if I add them first and then take the conjugate, or what? Conjugate them first and then add. You remember this formula also worked for subtraction, and interestingly also worked for multiplication and division. Now I want to ask another similar question here. Do you think if I exponentiate z first, meaning that if I calculate this first and then take the conjugate, do you think it will be the same if I conjugate z first and then raise e to power that? It's a better question, so I want to wait a little bit for you. Do you think, if it is true, you have to prove it. If it is not true, you need to bring a counterexample, yes? So the question is that, if I give you a z, you calculate e to the z first, you determine e to the z first, and then conjugate the result. Will it be the same if you conjugate the complex number first and then do this exponentiation? If it is true, you have to prove it. If it is false, you need to bring a counterexample for me. Okay, true or false?
True.
It's true. So how can you defend yourself?
Because you.
Do you mind if I start from the left side? Yes. So the left-hand side, yes, it is true. And it's a very nice formula. So left-hand side is, what is e to power z? I would say let z be what? X plus yi, yes? So this bar is that bar, but what is e to power z according to what we learned just now is e to power x multiplied by cosine of y plus I sine of y, yes? Okay, then how can I continue?
Write in the standard form.
You can write it in a standard form, or if you don't mind, let me use this rule, yes? So I can take this, put it here and put it there. So it becomes e to power x bar times cosine of y plus, I want to write all the details so that you're not confused. Okay, tell me, what can I write about this? E to the x bar. Why?
Because if you take the conjugate, you can view x as x plus 0.
Yes.
And if you take conjugate, it becomes x minus 5.
No. Don't say that, because that's exactly what we want to show. We still don't know that rule works. So what you are saying is that e to power x can be viewed as e to power x plus 0i. And then you say that, okay, when I take the conjugate here, the conjugate will be going here. That's exactly what we want to show. So I cannot use that. But the reason is different. Why the e to the x conjugate is equal to e to the x?
The number itself, e to x conjugate, is just x.
So why?
It's a real number.
It's a real number. Because e is real, x is real, so e to the x is real. And that's the reason that its conjugate is equal to itself. You cannot say because of this, because that's still under suspicion, you know. We want to prove it. Okay, but that's anyway. E to the power of x is real, so its conjugate is equal to itself. But what is the conjugate of this part? The standard way of conjugation. What is that? I keep the real part as it is. I change the sign and make it negative. Yes? Okay, then how can I continue? Because haven't I, what I want to show? I want to show that suddenly z bar appears. Hmm?
Just turning to backwards before we need to focus so you can accept the z will be
No,
x.
before that, I need one more step to justify that step. What you are right, but I have to justify that step. Yes?
Turn cos y to cos minus.
Minus y, yes, exactly, because I want to absorb this minus sign. In the De Moivre formula, I do not have negative sign, yes? So I have to get rid of that minus sign. So it is e to the x. Instead of cosine y, you know that I can write cosine minus y. And instead of minus I sine y, I can write plus I, but sine of minus y. So that is exactly the right combination for the De Moivre formula, but minus y is playing the role of theta. So this becomes e to power x, e to the power of I theta, but theta is minus y, so it becomes this. Yes? And this becomes e to the power of x minus iy. But what is this? This is z bar. So you can write, this is also a nice formula to remember. Okay. That's it, but let me see what else we can say. Okay, there is an exercise in the book. There is an exercise in the book. They want to show you, you're supposed to show this. If x is a real, let me write theta. If theta is a real number, we want to show that sine of theta is equal to e to the power of I theta minus e to the power of minus I theta divided by 2I. And cosine of theta is e to power I theta plus e to power minus I theta divided by 2. These are very famous formulas in complex numbers. It helps you to write sine and cosine in terms of exponential functions. This is an exercise in the book, but in the book they have used the letter x. It doesn't matter. So let us prove one of them. You can prove the other one yourself. So let us prove this one. This is an identity I want to prove. So it is better to start from that side, which is more complicated, simplified, and reach to the other side. So the right-hand side, what can I do? Instead of e to the power of I theta, I can write what? According to De Moivre's formula, cosine theta plus I sine theta. Yes? This is for this one. Minus, what should I write for this one? Here, you should view this as e to the power of positive times minus theta. So minus theta is playing the role of theta in the formula, in the De Moivre's formula. So this becomes cosine of minus theta plus I sine of minus theta, and then divided by 2I. And then the rest of it is just algebraic simplifications. So let us just do that. I don't need this pair of brackets, so let me remove it. But cosine of minus theta is cosine of theta. There is a minus sign going in, so it becomes minus cosine theta. Minus from sine can be pulled out. It becomes minus I sine theta, but there is another minus sign going there. It becomes positive I sine theta, yes? And then I have this divided by 2I, and then you see that's extremely simple because cosine and cosine are gone. I sine, it becomes 2I sine. And then divided by that 2I. And 2i's are cancelled, so this becomes sine theta, and that is equal to the left-hand side. And that's exactly, even this one is a little bit simpler, okay? But I want to leave it for you so you can do it yourself. Why these formulas are useful, I just tell you, this is not part of your lesson. this formula helps you to define sign of a complex number. For example, if I ask you, so this is the motivation behind of definition of sign of z. This is not part of the lesson, so optional. So if someone tells you what is the sign of a complex number, the sign of the complex number imitating this formula is defined to be equal to e to the power of iz minus e to the power of minus iz divided by I, and cosine of z is defined to be e to power iz plus e to power minus iz divided by 2I. Okay, I don't want to go through it, but that's the definition of sine of z and cosine of z. You see the difference, yes? Here z is a complex number. For example, using this formula, I can ask you what is sine of 1 plus 2I? Yes? Which we hadn't have so far. We only know sine and cosine of real numbers. And of course, tangent is also defined to be sine z over cosine z as usual. Okay? But that's optional, so you don't need to be bothered about it. Okay, there are some good exercises in the book, so let's solve some of them. So example, solve the following equations. Of course, in the book, they haven't asked you to solve, they have asked you find one answer. But I don't think it is hard to find all of them. So one question, I think that is still in the book, e to power z is equal to I. So we want to find all of them. In the book, they haven't asked you to solve, they have asked you find one solution to this equation. As far as you find one answer that works, that problem in the book is finished. But let us make it a little bit more interesting by finding all of them. So how do you think I will solve the problem? Do you remember the only thing that we had that in the last session was z to power n is equal to w. We were able to tell you how to solve these kinds of problems. If n is given, w is given, you want to find z. But here the right hand side is given, of course e is also given, you want to find z. So how do you think I will start solving the problem? Yes, so as usual, you can start with this sentence, let z be equal to x plus I, y. Yes? You remember here, I didn't start it with the standard form. I started with the polar form. I would say let z be equal to r cosine theta plus r sine theta, but for solving this, I start with the standard. So then, what can I write? I put it back here, e to the power of x plus iy is equal to I. Yes? Okay, e to the power of x plus iy is equal to I. We want to solve this problem. So what should I do here? It's a complex number, and that's also a complex number. So there's only one thing that we have to consider, and that is equality of two complex numbers. So the real parts should be the same, and the imaginary parts should be the same. Yes? But the point is that the real part of the real and imaginary parts of this is extremely simple. But this is today's lesson, so we need to know what is the real part and what's the imaginary part. So first of all, I write the formula for this. So do you remember it was e to the x times cosine y plus I sine y, yes? And that's equal to I. But then I multiply this in. If you don't mind, let me put I here instead of putting I here. And then on the right hand side, instead of I can imagine 0 plus how many i's? 1 I. And then I can immediately equate them. So this is my real part. This is the real part. They have to be equal. And this is the imaginary part. And that is the imaginary part. They have to be equal. Then what I have to do, I have to solve a system of two equations in two unknowns. Do you remember? It was not the case for these kinds of problems. In those problems, we had only one unknown. Yes? In this case, I have two unknowns and two equations. So, okay. How do you think I will solve the problem? But be careful. X and Y are real. So these things are not in complex numbers. They are in the realm of real numbers. X and Y are real numbers. So, yes?
Yeah, cosine of y is equal to 0 plus x to power e to power x
Cannot be 0. So whatever rules you had for the real numbers, it works here. Okay? So the product of two numbers is 0. Either this one is 0 or that one is 0. But we already know e to the power of x cannot be 0. So the only thing we can conclude from here is that cosine of y is equal to 0. Okay, but cosine of y is equal to 0. Where is y? Two places, yes? Here or there. But if I want to write all of them, either I can write two formulas, one for this dot, one for this dot, or I can combine them into one single formula. We had practice about that. So what should I write?
pi over 3 plus pi n.
Yes. So y becomes n pi plus pi over 2. But what is n here? N belongs to z. Okay, but we can say more here, not because of this is wrong. By looking at the second equation, we can say something about this n as well. Can you tell me what that n should be? Because n is an integer. In principle, it is either an odd number or an even number. But I am claiming for you it cannot be an odd number. Why?
If it was odd, then it would be
Yes, because if it is odd, where is it? It will be here. And sign of that number is -1. -1 times e to power x cannot be equal to 1 because e to power x is positive, and if this is -1, and then the answer is not working. So from here, that is completely correct. Any n is acceptable. By looking at the second equation, we realize that n has to be even. Is that right? So by checking this, so from these two together, I understand that n is even. Okay, so what does it mean? It means that n is 2 times q, where q is an integer. That's the meaning of being even. Okay, so I put this back. What is y? Y is equal to n, which is 2q, times pi plus pi over 2. Q belongs to z. But still, I haven't found the x. Okay, what is x then? Yes, if y is this one, what happens to sine of y? It becomes 1. And then it means e to power x is 1. But what is x? 0. Because that is the real number. So there is only one option for x, and that is 0. So what is z then? I was looking for z. Z is x, which is 0, plus y times I. So this is the answer to this problem. How many solutions are there, by the way? Infinitely many. And that's very strange, yes? So because if I have e to power x, let us say 5, in the real numbers, what is x? ln of 5. And how many of them are there? Only 1. But immediately when you go to the realm of complex numbers, that is, there are infinitely many complex numbers who e to power that number is I. Yes? Is that clear? Okay, let us do a little bit more surprising. So let me write number 2. Do you remember? That is also different. How many solutions were there for this equation? N. Not because there are, still in that case, then how many thetas were there? Do you remember? Infinitely many. But because sine and cosine were periodic, not all infinitely many give rise to different answers. But in this case, there are really infinitely many solutions. Okay, let me ask you this question. E to power z equals to minus 2. That's already surprising a little bit, yes? Whatever you thought about exponential functions in the real numbers, you should forget about them. Because if I give you this in Math 3C, what is the answer? No solutions, yes? There is no real x. E to power x is always positive, so there is no way that e to power x becomes negative 2. But let us try to solve this one. I want to wait a little bit for you, okay? So if you solve this one, there is also a good problem in the book. I will write it here, and then if you finish this one, start with this. 2e to the power of z minus the square root of 2 is I square root of 2. And that's also a good problem. But again, let me tell you, they are not asking you to solve. They are asking you to find only one answer. For example, if you want to find one answer, it is easy to guess. Yes? For example, you can say, okay, let me choose y equals to pi over 2. Then this works, and then x becomes 0. So here, be careful. The problem in the book is a little bit simpler because they are asking you to find one solution only. So even if you can come up with a guess here, that's okay. Let us start doing them because I want to finish. So what should I do here? So remember, for solving exponential equations, don't start with the polar form. Yes, start with the standard form. So again, as before, so let me skip this one. I will write let z be this, and then plug it back into the equation. I will get e to the power of x plus y equals to minus 2. And then I will try to find. And this is always the same, so if you don't mind, let me skip this one. I write the multiplied version. So it becomes e to the power of x cosine y plus e to the power of x sine y times I is supposed to be minus 2, but minus 2 can be interpreted as minus 2 plus 0. And then I get immediately a system. E to power x cosine y becomes negative 2. E to power x sine y becomes 0. And I hope that you agree. For the same reason, sine has to be 0 because e to power x cannot be 0. So this means that sine of y is equal to 0. What can I say about y? Here, up to here, without looking here, I have to write n pi, yes, where n is integer. But now, if I consider together that I have to, because that's a system, what can I say about n? Odd, yes? Because if n is odd, then cosine becomes negative 1, which makes sense. If n is even, cosine becomes positive 1, then I will have e to power x equals to minus 1, which will not work. Okay. By the way, let me solve this one a little bit differently this time. That was one way. Now I realize another way. We can compare the absolute values first. That is much easier, I think. I don't know why I did that in that way. That it worked, but I would say that if this number is equal to that number, then the absolute value of this should be equal to the absolute value of that. It will give me x first. Yeah, let me correct myself. It worked there, but I think this is more reasonable. So I take the do you remember we did the same thing for the other problem? I first found the r by comparing absolute values. What's the absolute value here? So let me write. And then this only needs, can you tell me what is the absolute value of this immediately? E to power x. The absolute value. So you see, I found x. So x is what? ln of 2. It was much better. So let us correct myself. It is easier. But then when I come here, I already know e to power x. Yes? I don't need to solve a system of equations because I already know x. E to power x is 2. So instead of e to power x, I put 2. Instead of e to power x, I put 2. And then I have to solve this system. But this is not a system because I have only one single unknown. I have to compare them. So I divide by 2, so cosine y becomes -1, sine y becomes 0. So I am interested in all possible y's for which cosine is -1, sine is 0. So then it should be an odd multiple of pi. So this means that y is odd multiple of pi. Yeah, so do you agree this is simpler? Because here I have to deal with a system of two equations with two unknowns, but here I got rid of one of them and then I'm left with just one variable. So, but the answer that you have to provide is what? Is z. So z is equal to x is ln of 2, the real part, plus this number multiplied by I. So that's a very interesting numbers. There are a group of numbers and n belongs to z. Yes? Okay, so let us do the other one using this. So remember, it is much better to compare absolute values first. Okay, in this problem, which is exactly in the book, so let us see how we can solve that problem. Of course, I told you again, in the book, they ask you find one answer only. So even if you can guess the answer, that probably is okay. But let us solve it here. But before doing that, what do you think I will do? I don't start by putting z there, yes? Yeah, move there and divide by 2, make it very standard, simple. So I will do this. So I would write 2e to the z is equal to square root of 2 plus the square root of 2i. Then I divide everything by 2. And then I would say let z be x plus yi. I put it here. Okay, so now let us follow this new method. I take the absolute value, but what is the absolute value of this? It's just simply this, but what is the absolute value of this? We calculate this 1 to power 2, 2 over 4, 2 over 4, which is 1. So x is clear. What is x? Is 0. Okay, now, what should I have now? I also write the formula for it. So e to the power x cosine y plus I sine y is equal to this number. But e to power x is 1. Yes, e to power x is equal to 1. So I can take it off. And then this one should match with this one. And this one should match with that one. And this is a famous angle. What is that? Pi over 4. But I am looking for all of them plus 2 pi. Yes. So y is pi over 4 plus 2n pi. N is an integer. So the answer that I have to provide is what? Z is equal to x is 0. This is my y. I multiplied by i's. So if you don't mind, let me factor a pi out. It's not important, of course. I would write 2n plus 1 over 4 times I. And then, of course, I write n belongs to z. So this is the answer to this problem. Any questions? No? Okay, so the next part of this lesson, as I told you, is related to polynomial equations with higher degrees. it is not directly related to the complex numbers, but sometimes complex numbers will be involved. So I would say that the topic of complex numbers is finished here. We need one more session to complete this chapter. And then I think it is better to have a quiz on this one as well to see how it goes. But because this is a long chapter, it might be that's a good idea to break it into two parts. So have two quizzes for this chapter. Might be that's a good idea. We will decide about that next time. Any questions? Thank you.